Exponential and logarithmic equations. All right, so it's time to pull it all together and to do some problem solving. Our objective here, we want to solve exponential and logarithmic equations, including applications. We know a lot. What I've listed here are the things that are applicable to this video. We know that the exponential equation and the logarithmic equation are related. Y equals b to the x. The exponential equation is equivalent to x is equal to the log base b of y. We know the property of equality of exponents. If b to the x equals b to the y, then x equals y. In other words, if you have the same base, the exponents are equivalent. Okay? And these are the property of logs that will be useful here. The product property, the quotient property, the exponent property, and this is the equivalence property of logs. If m equals n, then log base b of m equals log base b of n, and vice versa. So what are the general ideas? What are the general ideas for how to approach these things and solve them? When you're looking at exponential equations, solving them algebraically is often done by 1, applying the property of equality of exponents, which is right here, 2, rewriting them in their logarithmic form, which is here, and we've done that, or 3, applying the equality property of logarithms, which is right here. When you're looking at logarithmic equations and solving those algebraically, that is often done by either 1, rewriting them in their exponential form right here, or 2, applying the equality property of logarithms, which is right here. So some general ideas. Don't think for a minute that this is going to be something that you do one time and you've got it all figured out for all types of these equations. This certainly takes practice. I'm going to do a number of examples. I'm also going to solve these graphically using Desmos. So example number 1. Solve 5 to the x minus 1 is equal to 0.07, which is 7/100ths. This is an exponential equation. I have just a 1 exponent on the left here, so I will rewrite this using logs because I can therefore get at that exponent. So I know this is the same as the log base 5 of 0.07 is equal to x minus 1. The log allows me to get at that exponent. And so I add 1 to both sides. X is equal to the log base 5 of 0.07 plus 1. In that goes to a calculator, and it probably comes out as an approximation. I went to the thousandths place, negative 0.652. Algebraic check, put this answer in for x right here. If 5 raised to the negative 0.652 minus 1 is equal to 0.07, the answer is correct. Let's do a graphical. Let's do a graphical solution. Graphical. Okay, graphically, we can set both of these sides equal to y and see where these two graphs intersect. The intersection point is the solution. So y is equal to the left side, which is an exponential function. Y is equal to the right side, which is a constant function. It's a horizontal line. And we just look for the intersection. And Desmos makes that easy. Okay, let's take a look. And I'll come into here, hopefully get that straightened out. I'm going to put the home button here. Okay, go into this one. I'll do a y is equal to 5 raised to the. Now I want to point something out here. If you say, okay, you're in the exponent, if you say x minus 1, Desmos drops you down for some reason. It doesn't hold the minus 1 in the exponent. So we need to go back and we need to use parentheses to hold our exponent together. So 5 to the x minus 1, and I use parentheses, and now I have the entire subtraction problem in the exponent. So here's that purple curve. Let's do the second one, which we know is a horizontal line. That one's going to be y is equal to 0.07. And because I'm highlighted here, this is highlighting that horizontal line. Okay, if I highlight this one, it shows me where the y-intercept is for this equation, and it shows me a key point, which is the intersection point, negative 0.652, which is what I got. If I highlight the top one, it gives me the key point. One of the key points is the y-intercept, and the other key point, of course, is the intersection point, which is identical, negative 0.652. So solving it using Desmos is rather quick. Solving it using a graph is rather quick. Let's continue. I've got a number of examples because there are lots of different ways that this stuff, you kind of see this stuff. So we'll practice a number of those things. Let's solve 8 to the x is equal to 4 to the x squared minus 1. Well, not much I can do. These bases are different. Setting them up as logs means I'm going to be kind of mixing and matching things. But wait a minute. If I can get the same base, then I'll know the exponents are equivalent. Well, it turns out that 8 is equal to 2 cubed. So I can write 8 as 2 cubed, and so 8x is 2 cubed to the x, and 4 is 2 squared. So I can write 4 to the x squared minus 1 as 2 squared to the x squared minus 1. Now we still got a bit of math to do. We have a, we want to get these exponents together. Well, a base raised to an exponent, we multiply the exponent, part of our exponential rules. So this is 2 to the 3x. Same thing here, multiply 2 times x squared, multiply 2 times negative 1. And this is 2 to the 2x squared minus 1. Now I have the same base. 2 to the 3x is equal to 2 to the 2x squared minus 1. I have the same base, so I can use the equality property of exponents. If the bases are the same, the exponents are the same. And so I can write it like that and get out of those exponents. Well, that works, and you should recognize right here I have an x squared term, so I have a quadratic. Okay, go back to previous math perhaps. How do we solve a quadratic? Well, we set it equal to 0, so 2x squared minus 3x minus 1 equals 0. And then we can factor it if it's factorable, or we can always use the quadratic formula. This one happens to be factorable, so I can write it in its factored form. 2x squared can only be written as 2x times x. And I have, whoops, I made a mistake here someplace. Yes, I did. Okay, this should be a minus 2. 2 times negative 1 is minus 2. Sorry about that. Go back and make some changes there. I saw in my notes that I had a different thing there, so goofed. Let's go back and change that. So what this comes out to be is 2x squared minus 3x minus 2. The way you get a minus 2 is a 2 and a 1, 1 negative, 1 positive. And if you put the negative 2 here and the positive 1 here, it's factored. 2x squared minus 2, and then you have 4x, negative 4x, excuse me, plus an x is negative 3x. And now we use the product property, the zero product property. Anything times 0 equals 0. So this is equal to 0 when x is equal to negative 1/2. And this one's equal to 0 when x is equal to 2. So we have two answers, we think. X is either equal to negative 1/2 or x is equal to 2, or x is equal to this and this. We have two answers here. Again, we could solve this one by putting these numbers back into here. The 2 is probably simpler. 8 squared is 64. 2 squared is 4. 4 minus 1 is 3. And 4 cubed is 64. So the 2 is pretty easy to check mentally. The negative 1/2 would take me a calculator to do. Let's look at this graphically and find these two solutions, graphing them. So we'll do the exponential function on the left, so y equals 8 to the x, and we'll graph that. We'll do the exponential, I guess more of a, well, the next squared term, I'm not exactly sure what that's going to be. We'll do this one on y equals the right side, and we'll see where they intersect. It appears they intersect in 2 locations. Let's see if that's true. Alrighty, get myself set up here. Let's get out of here and out of here. And I'll go back to the home, which is 10 to negative 10. Left side, y is equal to 8 raised to the x power. That's a pretty easy one. It notes that it has one key point, which is 0, 1. And then the left side, y is equal to 4 raised to the, we have more going on in the exponent, so let's make sure to put parentheses in there to hold it together. X squared minus 1. That appears to be what's a quadratic curve there. Well, we can see already, again, we've highlighted the blue curve here, 4 to the x squared minus 1, and it has the key point on the y-axis, but more importantly, it shows the intersection here as negative 0.5. We came up with that one algebraically. Now, we're going to need to do a bit, it looks like, if we look at this, it looks like the blue graph is getting closer and closer and closer to the red graph here. And if I kind of work my way up, it may well, it looks like it intersects. So let's kind of bring this down a little bit. And I might can come out a little bit this way. And I can see here, okay, I found the intersection down here, but the blue is coming up and we can see them intersecting right here. I'll just tap, I'll tap either one to find the intersection point, it doesn't matter. And there's where they intersect. At that gray dot, I'll tap it again, and that's at x equals 2, which is what we came up with algebraically. So, and you can see again down here, the other gray dot where the intersection point is negative 0.5. So that worked out pretty well graphically. Let's continue solving some of these. Again, just some different forms of things you'll see. Okay, solve 5 times the log base 6 of 7x plus 1 equals 10. Well, here's one. We have the single log, so we can rewrite it in its exponential form after we move that 5. Okay, so we need to get the 5 out of the way. So I will divide both sides by 5. And I have the log base 6 of 7x plus 1 is equal to 2. So now I have log base b of y equals x. So now I can rewrite this one in its exponential form to get at the argument here. And we have that 6 squared is equal to 7x plus 1. Well, 6 squared is 36. Subtract 1 from both sides, and I have 7x is equal to 35. Again, 36. Take 1 away from both sides. I'll divide both sides by 7. And in this case, algebraically, x is equal to 5. I will allow you. I'll allow you to do that. In Desmos graphically. They should intersect at simply when x is equal to 5. Let's continue. Okay, how about a natural log problem with more than 1 logs? So, solve the natural log of 2x minus 1 minus 2 times the natural log of 4 equals 3 times the natural log of 2. Well, it sure would help if I could get the one natural log on both sides, because then I could use the equality property of logs. And I have a difference of 2 logs here, but I've got a 2 in front, so I got to move that 2. I don't have a difference of 2 logs. I need to move the 2 first, and that's equal to the quotient. So let's first off move these multipliers using the exponent property. And I'll come up with a natural log of 2x minus 1 minus the natural log of 4 squared is equal to the natural log of 2 cubed. Well, I can simplify those. This is the natural log of 2x minus 1 minus the natural log of 16, so that's just a number, is equal to the natural log of 8, and that's just a number as well. Now I have a natural log minus a natural log, so I can use the quotients of log property. The natural log of the first divided by the second is equal to the natural log of 8. Well, terrific. Now I have one natural log on each side, so I can use the equality property of natural logs. If I have natural log of A equals natural log of B, then A equals B. Okay? So I can drop those natural logs and come up with 2x minus 1 over 16 is equal to 8. Much nicer. Let's multiply both sides times 16 to get that out of the denominator. And I'll have 2x minus 1. 8 times 16, I hope, is 128. Let's add 1 to both sides. 2x is equal to 129. Let's divide both sides by x. And x is equal to 129 over 2, which as a decimal is 64.5. Okay, well, let's do this one graphically, because there's a lot going on here. So we have a left side. A left side's got a lot going on, but we just need to note what it is. So we're going to type it in exactly like it looks in Desmos. Okay, the left side is simply a number, 3 times the natural log of 2, so it will be a horizontal line. Y is equal to a constant. Okay, let's take a look. Come back into here. And I'll close out those two. Okay, equation 1 said y is equal to the natural log. We have a function for that, ln, 2x minus 1, and then close that parenthesis, minus 2 times the natural log of 4. And there's that graph right there. And now let's go to our second graph, which is y is equal to 3 times the natural log of 2. Okay, I'll close that. Well, there we have our graph. This one, obviously, the left side is obviously coming up and then growing ever more slowly. But again, it appears that they're going to, because it's a log function, they're going to intersect. The question is, where do they intersect? So I'm going to kind of bring it in this way, and you can see a little bit more clearly that this green is definitely growing and growing. It's getting closer and closer to the horizontal line here. We just need to figure out where that's going to intersect. And it's right here. You can see it here. It's intersecting right about there, so I can tap there. And Desmos says to me, that's your point of intersection. That's a key point. And there it is, x equals 64.5. So this can be solved with Desmos. Just put in the left side and the right side and graph them and come up with a point of intersection. All right, continuing. Let's get an application in here. According to one model, the number n of Americans in millions age 65 and older that will have Alzheimer's disease T years after 2015 is given by this exponential function, n is equal to 5.1 times 1.03 to the t. In what year will this number reach 8 million? Okay, well we want to have our n equal 8 million, and n is in millions. So 8 is equal to 5.1 times 1.03 to the t. Well, that's not bad. That's an exponential function, except I got this 5.1 hanging out here. And so before I rewrite it as a log, let's divide both sides by 5.1. So I have base to exponent equals number. I'll divide both sides by 5.1. That, of course, is 1. And I now have, let's see, 8 divided by, well, let's do this. Let's do the right side. The right side first is simply 1.03 to the t. Left side, I'll do the math, and 8 divided by 5.1 is, I think I went out to 4 decimal places, 5686. Now I have an exponential equation. I have just the one exponent piece over here. I want to get at the exponent so I can rewrite it in its logarithmic form. This is the base. So the log base 1.03 of 1.5686 is equal to the exponent. Okay, so if you want to look at this the other way, there's the base to exponent equals argument, which is right there. And so that's just a math problem. That goes into a calculator. And I get t equals 15.23 years. Now let's remember that t is the number of years after 2015. So this is number of years after 2015. So in what year, I'll have to do 2015 plus the number of years after 2015 to come up with approximately in the year 2030 is when I will see we will see the number of Americans who have Alzheimer's reach 8 million. Okay, let's do 2 more examples. Again, a bit more of the application type. Put my papers together here. When a camera flash goes off, the batteries recharge the flash's capacitor to a charge Q, according to Q is equal to Q sub 0 times 1 minus e to the negative kt. Q sub 0 is the maximum charge. How long does it take to recharge the capacitor to 90% of capacity if k is equal to 0.5? Okay, well, let's see here. I don't have a Q at the moment. I don't have a Q sub 0, but I do have a K, so it's 1 minus e to the negative k times t. So that's my equation. This is one equation in 3 unknowns. E is a number, of course. I can't solve this. So I got to come up with a Q and a Q sub 0. Well, let's think. We want to go to 90% of capacity. Q sub 0 is the maximum. We want to be 90% of that. So I could say if Q is equal to 100, if Q sub 0, the maximum capacity is 100, then Q would equal 90% of 100, which would equal 90. That's why I chose 100. That's one possibility. I could also say if my maximum capacity is 1 being a full, okay, then 90% of 1 is equal to 0.9. I could use either of these two. I just need a Q sub 0 and a Q because I need to have 2 of these filled in order to solve for a single variable. I'm going to choose this one. Why not? So I know that Q is 0.9, so I'll put 0.9 in for Q. I know that Q sub 0 is 1. Well, that's why I chose it, because there's no multiplication going on with a 1. Minus e to the negative 0.5t. Well, I can solve this one. Because I have one equation and one unknown, this can be solved. Obviously, 1 times anything has no meaning, so I can rewrite this is the same thing as 1 minus e to the negative 0.5t. Well, I kind of have an exponent, but I've got this 1 hanging out. So I'll tell you what, I'm going to move this to the left and move this to the right, and I come up with a positive e to the negative 0.5t is equal to 0.1. So I added this to both sides and I subtracted this from both sides. Now it's an exponential equation. I need to get at the variable. I notice it's base e, so I'll rewrite this as the natural log, because the natural log has the base of e. So the natural log of 0.1 is equal to negative 0.5t. Okay, you can see again here, here's the e to the negative 0.5t equals 0.1. I got to solve for t, so I'll divide both sides by negative 0.5. T is equal to the natural log of 0.1, divided by negative 0.5, and that comes out to be approximately 4.61. I don't see units, so I'll just write the word units. There you have it. There's that one solved algebraically. Of course, once you get to this part, you could do a y equals 0.9 and a y equals the right side and find the intersection point. Use x for t, and you'll get the same number, I'll bet. A last example, last application example here. Studies have shown that the concentration C in milligrams per cubic centimeter of blood of aspirin in a typical person is related to the time t in hours after the aspirin reaches maximum concentration by the equation. The natural log of C is equal to the natural log of 15 minus 0.20 times t. Solve for C as a function of t. My goodness, natural log of C is equal to natural log of 15 minus 0.20, I'll just write that as 0.2 because it's the same thing, minus 0.2. Okay. Well, it might be kind of nice if we can get these natural logs together, because then we can make it as one natural log. Certainly you got too many natural logs running around here. So I'm going to subtract the natural log of 15 from both sides, and I'm just going to leave it as the natural log of 15. I know it's a number, but if I do it as a decimal, I'll get an approximation. I'd rather have the exact number. So now I have a natural log minus a natural log, and we know that that's equal to the quotient of the first over the second. So this is 1 natural log of C over 15 is equal to negative 0.2t. Again, we're trying to solve for C, and so we're doing a little bit better. We remember, okay, now I have a natural log is equal to something, and so I can rewrite this in exponential form. Don't forget there's an e down here that's understood, and so we can redo this as an exponent. So e to the negative 0.2t is equal to c over 15. Base to exponent equals the argument. Oh, now I'm pretty good. Multiply both sides by 15, and c is equal to 15 times e to the negative 0.2 times t. I'm not so sure that one can be solved with a calculator. Well, there you have it. A wide variety of problems. As I mentioned at the outset, don't think that you're going to get to be an expert at this quickly. This takes practice, but if you'll make use of what I've just shown you here, make some mistakes along the way, you'll be just fine after that practice.